I am Professor Pratik Saxena from IIT Mandi. There are certain keywords in this particular topic, if you carefully observe. First is that we are going to talk about metal additive manufacturing. Second is that it has to be extrusion based. And third is it has to be lightweight. So how you can combine all these three things today we are going to understand in the next 1 hour. So this is our very beautiful campus located in Himachal Pradesh. You can see some nice pictures over here. So coming to the topic, how to manufacture lightweight structures and metals using additive manufacturing. So before I go further in my presentation, I would request you all to take your time and think about it, that if you as an engineer is given a task that you want to design a lightweight structure in metal or any alloy, how you are going to design it. So when we think about it, there are several options that come to our mind. The first and the foremost option that might have come to your mind is to choose some lightweight metal alloy, such as aluminium, for example. Someone might think that we can design hollow structures with optimized wall thickness to reduce weight. This could be another possible solution. Someone might argue that it's better to have some kind of grading, some kind of density distribution, some kind of material distribution throughout the geometry. That is another way of designing lightweight structures. Someone can say that we can probably use something like topology optimization for our structure. That is also possible. There is also another concept which you might, if you are familiar with additive manufacturing, you might have come across this term, which is lattice or cellular structures. So a lot of people, they incorporate lattice structures such as gyroid, honeycomb, and there are also some advanced structures such as TPMS structures which are available these days for making the overall geometry lightweight. Okay, so among all these things, we are going to focus on point number 5 for the next few slides. That if we want to have some kind of lattice structures, and if we want to manufacture them using metal additive manufacturing, how we can probably do that. We all must be using different kind of infill patterns in fused deposition modeling or fused filament fabrication process. It's a very common practice to give some kind of infill patterns while you are designing the part. But when talking about metal additive manufacturing, this might not be very common thing to do. I'll give you an example. So for example, if we have a closed lattice structure, so here you see that there is a gear, and the inner part of the gear, there is some kind of lattice which has been made. And if you like, you can see that the gear is closed from both the sides or closed from all the sides. That is why it is called closed lattice structure. So from inside it is hollow, but from the outside it appears to be a solid object. Now the question is that if I give a task to you to design this gear, to manufacture this gear using metal additive manufacturing, what are the probable options that you can think of? So most of you might say that laser powder bed fusion is one option for making this structure, while some other people who are working with wire arc additive manufacturing might say that we can also maybe think of making it with wire arc additive manufacturing setup. Okay, but the most commonly used technique, metal additive manufacturing technique, now metal additive manufacturing has advanced so much that there is no not only one technique for making these structures, while there are many number of techniques which are available. But most of us, if we have ever worked with metal additive or ever seen metal additive, they might have been familiar with LPBF, which is also popularly known as selective laser melting based technique for manufacturing the structures. Now the question is that, is LPBF technique a good solution for making a structure like this, which is closed lattice structure? Okay. What is the challenge? Why I'm asking this question? Because in my opinion, it is challenging to make such kind of simple structure using LPBF technique, such kind of simple structure which is hollow from inside. There is some kind of infill pattern given to it, and from outside it appears to be solid. What is a real problem? Why I cannot make this structure with LPBF process? There are three reasons that I have cited over here. The first thing is that metal powders used in LPBF often get trapped inside the closed lattice structure, making it nearly impossible to remove. Because you use metal powders in this process, once the structure has been made, the top layer, when you reach to the top layer, it will also be closed. So how you are going to take out the metal powder? So if the metal powder gets trapped inside the structure, then the entire purpose of making it lightweight by giving infill pattern gets defeated over here. Because a trapped powder that is present inside the structure, it is going to increase the part weight, and the purpose of lightweighting will be defeated. Sometimes if you are putting some kind of closed some kind of uh, complex infill pattern such as TPMS structure, if you are giving, you might need to have some kind of supports inside the closed lattice structures. And if there are some kind of support which are present, then using LPBF technique, these supports are very difficult or impossible to remove. So we can converge on this point that manufacturing closed lattice structure using LPBF is complicated. But what are the solutions which are available? Okay, so we understood until now that if I introduce infill pattern, I am going to make the structure lightweight, very commonly used technique. But if I take the most widely available technique which is there for metal additive manufacturing, which is LPBF, the solution becomes very complicated. So when talking about 3D printing process, I am pretty sure you must have seen this classification earlier as well, that there are 7 families of 3D printing processes. And if I ask you which is the easiest family to handle, or which is the easiest additive manufacturing process out of all these 7 families, no matter it is for polymer or it is for something else, but in your opinion, which is the easiest process? Most of you will say that FDM is the easiest process for me. I can comfortably handle FDM printers. Okay. So now we will come to the point that is it possible to 3D print your metal part using FDM printing or not? That will be the crux of our discussion in the next slides. Because this kind of technique is some technique which I might have seen, I might have experienced in my lab. The printers are also not very expensive. Printers start with something like 15,000 these days, 20,000. Some DIY kits are also there. So FDM is one thing which all must have experienced, but the problem is that FDM is used for making thermoplastic materials and not for metals as of today. Okay, here I have classified the AM techniques as per the materials which are available. So if you want to look into metals and alloys, then which kind of technique you can use? If there is polymers, which kind of technique that you can use? What I want to give information to you over here is that using the same kind of technique, it is also possible to manufacture in different materials. So the technique that I'm going to explain to you in the next slides, I call it MFFF or FDMAT, and you can see that I have listed it under two headings. One is metals and alloys, and another is ceramics. Okay. So with this technique, you can not only print in metal or alloys, but it is also very helpful if you want to switch to ceramic 3D printing. And what I'm trying to do over here, I'm trying to bring the best of the two worlds. That is, I want to combine FDM process for 3D printing of metals. Okay, because this process, FDM process, is very well understood and very easy to handle. It is also very cost effective. Okay, imagine if you have to establish a metal 3D printing facility at your institute. A laser powder bed fusion printer can easily cost you something around 1.5 to 2 crores, cheapest I'm telling you, and a good quality printer can easily cost you around 5 to 6 crores. And then there is also running cost that is involved in that. So in some printers, you have to put at least 8 to 10 kilograms of powder, even if you want to print a very small part. So the the cost per part will also be increased in that particular case. So those printing solutions, I would say, they are not very cost effective measure. But if there is something which can be brought under, let's say, 50,000 or under 1 lakh, under 2 lakhs, then most of us can afford to buy those kind of printing solutions. Okay. So now coming to the exact topic of today, that is extrusion based metal additive manufacturing. I like to call it as MFF or FDMAT. This is something, this nomenclature is not my personal nomenclature, but you will find this nomenclature in a lot of research papers as well. So one technique that I'm going to talk about it, FDMAT or MFF, which is also called as metal fused filament fabrication or fused deposition of metals. And this technique gains its inspiration from another manufacturing process, which is metal injection molding process. Now, I am pretty sure that most of you might be familiar with an injection molding process where a polymer is used and the parts are molded using an injection molding machine. But what is this metal injection molding process? I'm sure that most of you might be unfamiliar with what is the metal injection molding process and how does it work. So before understanding the extrusion based metal 3D printing, it becomes very important to understand that how a metal injection molding process works, because our entire process is draws its inspiration from this particular process. Okay. Now, this particular process, metal injection molding process, this is very similar to the plastic injection molding process. Okay. And what happens in plastic injection molding process? There is a lot of plastic pellets that are being used. And in this case, because you are going to 3D, you are going to do metal injection molding, there fine metal particles replace the significant amount of plastic. But that is not all. It is not that we are only putting in metal powder over there, but in addition to that, we will also include other things which are called as binder, thermoplastic elastomer, and surfactant. So what I'm trying to convey over here is, if you read first point very carefully, it is written that it replaces a significant amount of plastic. It is not written over there that it replaces all of the plastic. Understood? So this means that if I have 100% plastic pellet, which I was earlier feeding to the plastic injection molding machine, now I might be replacing 80% of that plastic or 85% of that plastic with metal powder, and the remaining will still be plastic. You will understand why I still need plastic in this process and why I cannot only run it with the metal powder. But other than plastic part, you will also require, because of the nature of the process, you will also require a few other things, which for now we can call it X additives. Okay, we need some kind of additive which we can represent by X. And these X additives are some kind of binder, some kind of thermoplastic elastomer, and some kind of surfactant. They are all contributing to the remaining plastic part that is being fed in the metal injection molding process. Now, what is a binder? What is this? What is this? We are going to discuss in the next slide, but next few slides. But for now, we can understand that there is a unique recipe that I need when I'm going to do metal injection. So the metal powder, which forms the majority of the constitution, plus all these additives, they are compounded using a twin extruder and injected into the mold of desired shape. The part made out of molding is called as green part. Now the part which is being formed in metal injection molding process, that part is basically majority of the metallic part plus all these additive part, and this part is called as green part. I can also quickly show you the flow diagram so you can relate. So what I'm talking about here is I'm talking about these steps. Okay, so over here you are going to make a unique recipe, and then you are going to feed that unique recipe to your injection molding machine. Everything is being fed into the mold, and after the injection molding is done, a part will be produced. Now this part, like you have seen the recipe, it will consist of your metal plus X additives which will be there. And if I want a pure metal part from metal injection molding process, all these X additives which are being present over there needs to be subsequently removed. So then we have some subsequent post processing steps after this injection molding, that we do some kind of solvent debinding, then we do some kind of thermal debinding, and then we also do some kind of sintering process. So these three processes that I have listed, we are also going to talk about these in detail, that these three processes will only help us to remove all the plastic part which is being present and to bring down together the metal part. See, when you have metal powder, and if you want to join, if you want that all heat to the system, okay, in some cases heat plus pressure is required, okay, but the kind of temperature that we are talking over here for metal additive manufacturing, that temperature is will be something around, or that for that example, for example, metal injection molding, the temperature range that I'm referring to over here is something around 1300 degrees, 1400 degrees, 1500 degrees, depending on the kind of metal powder that you are using. But one thing important that we have not acknowledged over here is that this temperature range, which is beyond 1000 degrees centigrade, this temperature range is too much for the plastic material, because plastic will most likely evaporate at this stage, or most likely it will degrade at this particular temperature. And at that point, when you are, let's say if you are supplying 1300 degrees centigrade all at once, your metal powder will not start fusing in a fraction of second. It will take time for the metal powder to fuse together, but your polymer might evaporate in a fraction of second. So then your entire part will be collapsed. So that is why it is very, very important that we maintain a particular kind of cycle. We don't remove everything at once. That is the reason why you see different steps over here. So coming back to what I was discussing, so I was telling you that the part that come out of injection molding is called green part. The green part is then taken to something called debinding chamber, where your thermoplastic elastomer is removed by chemical and thermal debinding. Okay, so we are not removing all the X additive that I have referred over here, but a fraction of it is taken away in the solvent debinding process. And the part after debinding is called as brown part. The brown part is then sintered in a furnace vacuum chamber in a shielding environment to get a metallic part. So let us try to understand this entire procedure, and let's try to digest it with the help of a video. So that will also help you to understand that how this entire philosophy is working. So I'll play my video now. I hope the video is being played already and you are able to see.
Yes, sir.
Yes. So over here we can see that the powder is being fed from the top of the hopper, and it is being pushed forward into the machine. The next is debinding and sintering. So we have seen that when the debinding process is being happening, when it is being dipped in a particular kind of solvent, the thermoplastic elastomer is going away, but the metal powders, they are not fusing together, which is true because we are only dipping them into a solvent. We are not giving it any kind of heat. If I want the metal powders to fuse together, then I need to supply some kind of heat which is in the order of 1300 degrees Celsius or 1400 degrees Celsius, depending on metal to metal, what kind of alloy you are using. Okay, and if you have carefully observed, you must have also seen that the parts also shrunk down in the process, which is also true because if there is 85% of metal powder and the remaining is the polymer, then the entire polymer will go away, and when the metal powder will shrink, the final part will be of metal. So when the polymer goes away, the the final part will definitely be smaller than what you have already designed. So these kind of thing you have to compensate while you are designing the CAD model. I will replay this rewinding and centering once again because this is the extremely important point in our entire discussion today. Yes. So in this way, the final metal part is obtained. Now coming back to our concept of MFF or FDMAT technology. So if I want to combine FDM and if I want to take inspiration from this process, metal injection molding process that I have shown to you, now you have understood that it cannot be done without subsequent steps. Subsequent steps meaning solvent debinding, thermal debinding, and centering process. Okay, these subsequent steps you cannot omit. These steps will certainly be there. There will one step, instead of injection molding we will now have 3D printing, but there is also one more step which is filament fabrication. And this is also very crucial because you see, if you want to use a conventional FDM printer, the first thing what do you need over here? You need a feedstock, and the feedstock is in the form of a filament, a wire kind of thing, which can be wound on a spool. Okay, but you also have to understand that this particular nozzle head that you see over here, in a conventional FDM printing, it supplies some temperature. Okay, and what are the temperature ranges that this kind of nozzle can give? It is something around 180 degrees and Celsius, maybe 200, 210, 220, because most of the polymers, thermoplastic polymers, they are processed at this particular temperature. If you talk about some kind of advanced polymers, for example, PEEK, then you might need temperatures in the order of 400 degrees, 450 degrees. But in this particular nozzle, I will never need temperature in the order of 1000, 1200, 1500. No, that won't happen. So what I'm trying to convey over here is that this nozzle is something capable enough to give a shape to a polymer part. Okay, so what I'm going to do now, so I will try to understand that how first this feedstock is being made. Okay, and how I can optimize my nozzle so that this particular thing is printed. Okay, I can give you a quick hint over here. So when I'm making a filament part, there is not only metal powder that is over there, there are also some kind of additives that I have mentioned there. Remember, I told you then that in the slide, it was written in the first point that you are not replacing all of the plastic with the metal powder. You are only replacing the fraction of that with the metal, fine metal particles. The remaining is still polymer part, the remaining polymer granules, and then there are some kind of other additives. So we can now talk in a little bit details that when I am going to formulate my filament, what exactly I would need. See, you also have to understand that this wire that I am talking about, this wire is not like the wire that you use on wire EDM process. It is not the same wire. This wire is also not a rigid wire. This wire is not like a copper wire. This wire is something which looks like a regular filament, regular plastic filament. Okay, so it is something which can be wound on a spool. You also have to think this in terms of let's say if there is 85% of metal powder which is there in the filament, if this amount goes into the filament, then the metal powders have not fused in together yet. They are still sitting there as a powder particle. Now, what will be the repercussions of that? That if I try to wound that on a particular spool, this material will be highly brittle material. So if I try to put it on a spool, it will most likely it will break. So there will not be any kind of flexibility that will be there. Okay, I hope you are trying to. I hope you are following it. We need not only to make a filament, but we also have to give it some kind of flexibility. Okay, so let's very quickly go through what are the constituents of these filament fabrication. So first is of course your metal powder, which is the primary material for filament fabrication. Okay, and this powder material depends on which metal we are talking about. Now, a good thing about this particular process is, which is particularly advantageous, is that you might have heard from a lot of people, or you might have seen in the research papers as well, with laser powder bed fusion process, it is very challenging to print copper parts. Okay, I'm not saying that it is impossible. People have reported that they are able to print the copper parts using LPBF. That is well established in the literature, but it is challenging. You cannot use a cheap laser source, a low power laser source for 3D printing of copper, because copper is highly reflective material. It is going to reflect back your laser beam, and your laser source will get burnt away very easily. Okay, but there are specially designed laser powder bed fusion printer with which people have printed copper part, but again it is expensive. But with this kind of philosophy that I'm teaching you today, it is independent of what kind of metal powder you are using. Okay, it doesn't matter whether you want to use copper. It doesn't matter if you tomorrow you decide that I want to use titanium. If day after tomorrow you decide, okay, I want some kind of high entropy alloy or something else, some kind of new composition, it is certainly possible, which might not be possible in laser powder bed fusion. Okay, but again what is important is that you identify the exact recipe. Okay, what it is going to what it is going to be there. You identify the specific sintering cycle. You identify how I am going to debind it. These things will play a role, but what I'm saying in theory is that it is very much possible that you can 3D print any kind of alloy using this particular philosophy. So metal powder bed in of course in this filament fabrication you need metal powder that we have already discussed. Next is thermoplastic elastomer. Thermoplastic elastomer is something that will allow some kind of flexibility to the filaments. It will its contribution is that it will help that the filaments can be wound on a spool. First thing, and second thing is when I'm going to put this spool on a 3D printer, on my FDM printer, this thermoplastic elastomer will be very, very useful in giving shape to the structure. So what could be this thermoplastic elastomer? I can just tell you it could be something like PLA, it could be something like ABS, it could be something like nylon. Okay, so here I have written that thermoplastic elastomer helps in giving flexibility, and it is of course very useful in 3D printing. And high temperature thermoplastic elastomer makes extruded filament properly bond with the previous layers. Okay, so entire 3D printing that is happening with our printer, it is because of this thermoplastic elastomer. It is not because of this metal powder. Metal powder is just sitting over there. Okay, even if I'm printing a cube using my FDM printer with this kind of philosophy, the metal powder in that cube is just uniformly distributed. That's all. It has not bond yet. The sturdity in the structure has come because of the plastic part, because of this thermoplastic elastomer. Okay, you might also need something like binder, for example. Why I need something called as a binder? Because if you have observed carefully in this particular slide, here I have not written one single debinding, but I have written two types of debinding. Okay, one is solvent debinding, Another is thermal debinding. Okay, so solvent debinding meaning that I will dip this part in a particular type of solvent. That solvent can be water, that solvent could be acetone, that solvent could be chloroform, that solvent could be any kind of weak acid. Okay, but when I dip in that solvent, imagine what would happen if that particular solvent eats up your entire polymer that you have added to the structure. What will happen? Your part will collapse, because at point number 3, at this particular stage, the metal powders have not yet start fusing together. So when the metal powders have not started yet fusing together, then if we put it in a solvent, then what will happen? The entire thing will collapse. Okay, that is the reason why I have divided this debinding in two particular stages. That in first step I will take away some part. Okay, I will not eat up all the polymer, I will eat some part. Most of the part could be, but there will be something that will be still be remaining, and that something will act as a backbone and will give structure its shape. It will not let the structure lose its shape. Okay, and that something which remains over there could be taken very easily at thermal debinding step, because thermal debinding step is a step where you are giving heat. At that heat, most of the polymers will probably evaporate. Okay, so that is the reason why I'm using a binder over here. The binder acts as a backbone, and the binder, the only thing that is required from binder is that it lets the part to retain their shapes after the solvent debinding has happened. Okay, and when I put everything into the sintering furnace, at there what will happen at those temperatures? The binder will also evaporate. There is also one more thing that I haven't told you until now. There is also one more advantage to this kind of approach, is that let's say if I have made a cube, and when I have dipped that cube into a solvent and partial debinding has happened, something has gone out. A good thing is that whatever has gone out, it would have created some kind of escape routes. It would have created some kind of channels. Okay, at also at the interior and also at the top of the surface or on the sideways. And these kind of escape routes, these kind of tunnels, these kind of things will easily allow the binder to go out from these escape route. Now imagine what would happen if I would have not created these escape routes. I will quickly show you over here. If I have not removed this thing, what would happen? I will see this kind of swelling on the structure. The polymer inside the material wants to go out, but there is no escape route that has been created. So what will happen? It will get trapped inside and it will swell the structure. So this is, if you are seeing this kind of swelling on your structure, that means your binder has not been completely removed and your powder has centered. Okay, let's come back to our discussion again. The one more thing that you would need over here is something called surfactant. So why do I need surfactant? You see that I told you that you also have to make a filament. Okay, and imagine while making a filament, if I have put all the polymer, all the metal powder, imagine how difficult it will be to push that thing through a small nozzle. Okay, so the viscosity of that entire recipe would be very, very high. So which also means, I don't know if you have seen ever seen a extruder or not. Extruder looks something like this. Is a single screw extruder. So from top you have fed this entire recipe, and there's a screw, and there's also a motor. Okay, and this motor is rotating the screw, and whatever is being fed over here is being pushed out. Okay, and then this entire thing is also heated from both the ends. So when this polymer that is being present over here changes its phase, and they come out like a filament. So if there is lot of metal powder, then it will also be very, very difficult to push this thing forward, because the viscosity of the system will be very, very high. So that is why you also need to put a lot of pressure on the motor. And to avoid this kind of thing to happen, to manage the torque requirement that is will be required by the recipe, you mix some kind of surfactant into the entire recipe. Okay, so here I have shown to you, this is a single screw extruder that I am showing to you. Okay, I have also shown twin extruder that is there. Okay, there's one thing that I have mentioned over here, compounding. There is something that I have mentioned over here is iterating method. Okay, let's try to understand these two things. So when a filament is being formed for the first time, it might be possible that all your metal powders, they come together in one particular zone. Then in this particular zone there is no metal powder at all, and then in the third zone the metal powder again, they are coagulated, or not coagulated, but they are like present in a very specific zone. Now what is the problem with this particular kind of thing is that the metal powder are non-homogeneously distributed, which I don't want, because later on I'm going to use the same filament for 3D printing my part. Now imagine if I'm making a cube, at some place there is a lot of metal powder that is present, while in other place there is only plastic which is present, there is no metal powder at all. Now when I'm going to do the debinding and sintering thing, wherever there is no metal powder, wherever there is only plastic thing which is present, it is going to distort my structure completely, because there was no metal powder which was present. What would have sintered? What the plastic which was present there has eventually gone away. So it is very important that you maintain the uniform distribution of metal powders. If the metal powder distribution is uniform, only then your structure will shrink uniformly. The structure will be will be prepared in a nice and uniform manner. And for that reason we use the iterating method. So what do I mean by iterating method? So when you are putting this entire recipe through the hopper, and then when the filament is coming out, you pelletize that filament, you cut it into small pieces, collect it, and feed it again to the hopper. You do this cycle at least 6 7 times, 8 times, and after that you will realize that your filament that is coming out is the it does have a uniform composition of the metal powder, which is very important for us. Okay, now there are several things which people might be thinking, and you also might want to know, does powder size has a role to play, the powder content has a role to play? Yes, it does have a role to play. Everything that is in there has some or the other thing, some kind of role to play. If you increase too much of the metal powder, the viscosity of the entire recipe goes high. Okay, the viscosity increases drastically, and that is the reason why we are also using surfactant. So tomorrow if you say, sir, okay, let's want to put 95% of the metal powder over here, it will be extremely challenging to make the filament out of it, and the filament that will come out, it will be of highly brittle in nature. If you touch it, it will break very easily. So you cannot just randomly think of any number and you can just put in over there. The amount of powder in the feedstock affects the rheology of extrusion. As the percentage of powder increases, the viscosity of extrusion correspondingly increases. Okay, but it is also true that in the feedstock, the powder percentage has to be relatively higher, because this is the thing at the end which is um, going to uh, going going to form your metal part. Okay, for the final part to shrink less and have high density at the end of sintering, having the maximum powder percentage in the feedstock is necessary. Okay, and this thing is also written over here: a feedstock with high powder content filaments with high inhomogeneity, making them highly brittle. If there is very high powder content which is there in the filament, then it produces those filaments with very high inhomogeneity, and the filaments, they are very brittle. Okay, and of course all these things, powder size, powder shape, they have some or the other role to play. We don't have time to discuss all of that today, but I can tell you that there are a lot of things. It's not very straightforward to make a filament, even though I have taught you how to make the filament in the most detailed manner. So once you have your feedstock ready, you also want that your filament should have a uniform diameter. It should not be like that the diameter in one zone is something else and another zone is something else. That is also not required. The layers that are being formed during 3D printing, they should also be able to fusion together. That is also very, very important. Okay. So coming to the second thing, which is the 3D printing of green part. Now this is pretty straightforward, that once you have this feedstock ready, then you can feed it on your normal FDM printer, and your normal FDM printer will be able to print it with ease if you have made the filament in the right manner. Now, there is one thing that I haven't told you. You might ask me that, let's say if we buy something of 30,000, 35,000, 40,000 printer, can it 3D print can it 3D print my this metal polymers filament? The answer will be yes, it will be able to 3D print, but what will be the problem? The problem will be that you will see that the nozzle part which is being there, then this is wearing out frequently. Why? Because in the filament there are a lot of metal particles. The metal particles are going to rub again and again with the metallic with this particular nozzle that is over there, and then it is going to worn out. So you will see that it might worn out in a day, in 2 days, in 3 days. So that's wearing will happen very soon. So what change I have to make in my cheap 3D printer is this particular head I want to replace, this particular nozzle I have to change. I cannot go away with the cheap nozzle. I need something like a hardened nozzle where I can comfortably handle these kind of filaments which have metal powder filled in it. Okay. So this is the criteria which is there. If you want to buy from the market, there are also FDM printers that can print this kind of filament. Ultimaker is one of the example. Race 3D is another example. So these kind of printers they sell in the order of 8 lakhs to 10 lakhs. These kind of printers can comfortably handle this kind of filament. Okay, but if you want to try something on your own, it's better that you design something by yourself and you use an optimal kind of nozzle thing. A good thing about this particular process is that you can very easily make it as a hybrid additive manufacturing process. Hybrid by the word hybrid I mean additive subtractive manufacturing process. Okay, so on my 3D printing head where the nozzle is being kept, I can also maybe attach something like a milling cutter over there. So when the part is being formed, first of all, here you can see when the part is being printed using extrusion. When I need to mill out something, my milling cutter comes in, and then it will give a shape. Then again, my nozzle will come into the picture, and it is going to print the part. Now, this will help you a lot when you want to do hybrid additive subtractive manufacturing, and then this will also cut down the need to post process the part. Sometimes we do the subsequent milling operations once the entire part has been printed. That will not be needed. You can do it at the time when this printing thing is happening. Of course, then the next subsequent steps will come. There will be debinding and sintering cycles that will come into the picture. The green part will be formed from here. Then it will come to the brown part, and once it has been finally sintered, then you will get the final part. Which, if you want, you can also, I don't know, if you want to polish it, you can polish it. If you want to color it, you can color it. If you want to do whatever, you can do those things. Okay, but this is one scheme that I wanted to tell you. We talked about this very briefly. We talked about what is a debinding. So debinding is divided into two parts. One is the solvent debinding and one is the thermal debinding. In solvent debinding, I will take away majority of the plastic part, my thermoplastic elastomer. So whatever is being used in the recipe, if you are using, let's say, PLA, then you have to pick up a solvent in which PLA is soluble. You also have to remember one thing, that this cannot be same as your binder. If you are using PLA as your thermoplastic elastomer, then your binder cannot be thermoplastic elastomer, because otherwise binder cannot be PLA, because otherwise everything will go away in solvent debinding step, and you will be left with nothing at thermal debinding. So thermoplastic elastomer is different, binder or backbone is different material. Another thing to consider is, when I am doing debinding, when I am putting into some kind of solvent, then I want that solvent, be it chloroform, be it water, be it acetone, be it whatever, it should only be reactive towards thermoplastic elastomer. It should not be reactive towards binder. Your binder, whatever it be, it should not be soluble in your acetone, in water or whatsoever. The binder must not be reactive towards it, because otherwise everything will collapse. Okay, so now you have understood that solvent debinding is carried out before thermal debinding. Okay, and also a porous network, a structure like what I was telling you, escape routes have been created. So when you are going to put entire thing into a sintering furnace and operate a sintering cycle, then what will happen, whatever is being there, whatever is being trapped inside the binder part, it will go out through those escape routes. The metal powder will sinter together. Now you might be thinking that this process is very instantaneous, that I dip my green part in a solvent and within 2 minutes, 3 minutes, this debinding will happen. The answer is no. This debinding is gradual. This debinding is slow process. Okay, whatever literature I have seen, whatever process we have been working on, people do this debinding in 4 hours, 5 hours, 8 hours. Some, in some cases, in this picture you have seen, you can see that we are doing it, we are showing it in 12 hours. The removal is gradual. Okay, and once this thing that is your thermoplastic elastomer, which is shown by light pink part, if you observe carefully on the screen, then this thing goes away slowly and gradually, and you see that white spots are being created in this last structure. Now these white spots are nothing but the escape routes. So when I'm going to put this structure into a furnace, then whatever reddish or dark reddish thing you see over here, this thing will try to evaporate, and using these structures or network of structures, it will go out, like I have shown in this particular picture, that in thermal debinding, this entire thing, this binder that I am that is there, they try to go out, and at the same time what is happening, the metal powders which are present, they try to form a they try to fuse together with the necking phenomena. Okay, so this is what I have mentioned over here. And in this particular picture, you can see that this is my brown part when I have put it into a sintering furnace. Now this sintering is, again, it's not just a single step. It is not just done instantaneously. It is something that will require some time to happen. A particular type of cycle needs to be operated. Okay, and once that has happened, and if everything was homogeneous, then your part will be formed, and your part will of course be smaller than what is intended, because everything which is other than metal has now gone away, and what you are left with the metal part only. Okay, someone might talk about, sir, how much porosity will be there in the structure. I have not tried to observe it myself until now, but what I have read in the paper is that the porosity will be comparable to the laser powder. It's comparable to the porosities that you are obtaining in the laser powder bed fusion process. Okay, so here I have tried to show you, this is a two-sphere sintering model, that how the two powder particles, they are trying to fuse together. And remember, I told you everything has a role to play. If there are fine powders compared to coarser powder, they have a role to play. If they are not completely spherical, if they have irregular shape, that also have a role to play. So everything has some or the other effect on the final shape of the part, how quickly and how efficiently this centering process is being happening. Okay, so this is the entire process being summarized over here, and in the end you can see that once the part has sintered, your entire final thing is a metallic part. And if you want to post process it, if you want to machine it, color it, whatever you want to do, you can do it. You can see that this gray thing is your powder particle shown over here. The the dark green thing is your backbone, and the light green is soluble binder. So first your soluble binder goes away in here. The gray thing is the next thing which goes away. In the dark gray thing is the dark green thing is the backbone, which goes away in the next step. And then in the centering is the final centering of the part that happens. So this is all about today's discussion that I want to put up. We have also made a very nice review paper. It is not shown in this slide, but I have published a paper in Composites Part B, which is the review of this particular technology. Our lab also works on end-to-end technology. We work in the filament fabrication. We work in 3D printing of the part. We work in debinding, sintering. So we have PhD students and master students working on end-to-end solution. So if you are interested to work in this kind of technology, you are more than welcome to approach me. I have put my number, email, and also LinkedIn ID on there. Please feel free to connect me on LinkedIn. I'm very active over there. Our lab website, our web page is also there on LinkedIn, so you can follow that. So this is one theme in which we are working, but we are also very active in continuous fiber reinforced 3D printing. So if you are interested in something like that, where you want to um, work on continuous fiber reinforced 3D printing, we are one of the few groups in India who work in that technology. So please feel free to reach out to me. We are always in need of good postdocs, good PhD students. So whatever is your interest, just feel free to write to me, and then we can discuss what are the opportunities we have to offer. So that's all for today's discussion. With this, I would like to end my presentation. Thank you very much for your patience listening.
Participant may write in the chat box for any query. So we have one or two queries over there,
Mhm.
and the
So,
first one
yes.
is that what is the effect of the temperature difference between the metal powder and the polymer on wire formation during the extrusion process?
Yes, so I can also see Vishal has asked this question.
Yes, sir.
So, Vishal, this depends on. So, you see, when you are making a filament, I have said wire, but it's basically a filament similar to a polymer filament. So, whatever processing steps you are going to take, this is in accordance to what you do for the polymer processing. So, I think you have what you want to say is this: what temperature should I keep? Because metal is also there. You don't have to worry about metal, because metal, just see metal as an additive who is sitting over there. It can, that additive could have been graphene, that could have been nanographene, that could have been sawdust, that could have been anything. But my intention is the polymer that I am mixing over here, which is called thermoplastic elastomer. So if that polymer is PLA, I will probably set my processing steps as per the PLA. If it is nylon, according to nylon. Okay, the temperatures, if you want to know the temperature range, it will be something around, I don't know, maybe 120, but something surely below 200 degrees. We won't go beyond 200 degrees, because I'm not concerned about metal. Like I told you, I'm not forming a metal wire. I am forming a polymer wire, a polymer filament. Inside, the metal particles are sitting in a homogeneous manner. Okay, the second
Thank you, sir.
question. Uh, yes, the second question is from Avinash. How do you determine the appropriate sintering cycle for different metal powders used in the filament? So, Avinash, this is something that we look on hit and trial basis. Sometimes we take inference from the research papers. There are not too many research papers available in this technology. If you look into the research paper in last 3 4 years, some papers have started coming up. So we take inspiration from that, but otherwise it's more or less on the hit and trial basis that we do. Yes. Anybody
Any other?
else?
I think, sir, there is no other queries. So thank you, sir, for your very insightful words about the concept and the talks. So we are looking forward for your further collaboration, sir. Once again, sir,
Thank you.
thank you. Thank you very much.
Thank you. Thank you very much, sir, for inviting me. And these sessions are usually very, very helpful. And it's a good opportunity to interact with your group and also with the participants. So thank you for
Right.
considering me for this talk.
Okay. Thank you. Thank you,
Thank you.
Pratik.
We'll be in touch. Thank you. Thank you, sir. Okay.